Okay, in this video, we are going to talk through exponentials and logarithms just as functions. And then in 5.3, we will take derivatives of them. And then 5.4, 5.3 and 5.4 will take derivatives. So this is basically just supposed to be a review of the functions in general. So an exponential function has the form f of x equals b to the x. So if that base, that's what the b is, if that's bigger than 1, then your exponential function looks like that. If the base is smaller than 1, it's called exponential decay. This is exponential growth. If the base is smaller than 1, then it's exponential decay, and it looks like this. That's b less than 1. This is called exponential decay. And so b is greater than 0. There could be a constant in front that could take on the negative, but the base itself is positive and it isn't 1. I don't have a C and an R. Maybe this is supposed to be f of x equals the constant times b to the r. Okay. So let me put that up here. The domain of these things, you can look at these graphs and see, oh, sorry, I didn't realize that moved. You can look at the graphs and see that the domain is all real numbers, left to right there. Well, the range is going to be from 0 to infinity. The y-intercept, whether it's exponential growth or decay, here is 0, 1. They both have horizontal asymptotes at y equals 0, the x-axis. They approach the x-axis but don't touch it. If b is greater than 1, then the slope is positive and it's concave up. If b is less than 1, then the slope is negative and it is concave down. Nope, up, both up. Up like a cup in both. Okay. So we're going to use this idea to do some like business problems. So the compound interest formula for principal P invested at an annual rate of R compounded n times per year for T years is given by this formula. The accumulated amount equals P, the principal, times 1 plus the rate as a number divided by n to the nt. Then the continuously compounded is going to be A equals P times the number e to the RT, PERT. That number e is like 2.718, blah, blah, blah. It's kind of like pi in that it is not rational. So it's just a decimal that goes on and on forever. Okay. So let's use that to talk about some business problems. So if $5,000 is invested at 4% interest, what will the future value be at the end of 10 years if the interest is compounded monthly? That's A. So compound interest, remember we're going with A equals P times 1 plus R over N to the NT. And we're going to plug in the stuff that we know. So we have $5,000, that's our principal, that's invested at 4%, so 0.04 for R. It's compounded monthly, so N is 12. And then we want to know what happens after 10 years. So T is 10. And then if you plug that into a calculator, you'll get that your accumulated amount is $7,454.16. The biggest problem probably would be when you type this into a calculator. I would probably even like do this. You wouldn't need all these parentheses, but like that. So when you put this in your calculator, some of you have those like an 84. You probably don't need to do this, but an 83 you would. You'll hit that little up button, to make that an exponent. Anyway, put that exponent in parentheses if you don't have a calculator that has that box, I don't know if y'all know what I'm talking about. If you have the calculator, so you will. If it has this box, you can just type 12 times 10 up in the box. But if it doesn't have a box, you're going to need parentheses. You would do this like raised thing, 12 times 10, and then close them. Okay. So once you do that in the calculator, you should get $77,454.16. If you do not get that and you need help with your calculator, send me an email. B, we want to know what happens when it's compounding continuously. So the more often these things are compounded, this is probably a thing that you already know since you are business people. The more often that this is compounded, that's how often it's adding the interest on or calculating interest on it. So the more often that happens, the more money it should make. So if the rate and everything is the same, the thought here is that the number we get with B, that accumulated amount with B, would be higher because it's adding on the interest more often. So we're using A equals P times E to the RT. That's the continuously clue there. So A equals 5,000 times E to the rate is the same, 0.04, and time T is 10. Again, maybe in your calculators, it would help to write this like this. Okay. I'm going to have to do this in Desmos because I think my work that I have is wrong. So let's check this. If we do 5,000 times E to the 0.04 times, nope, listen to my own self, put parentheses around that, times 10, $7,459.12. Okay. So it does earn more, not a significant amount more, but it does earn more. So that's good. All right. So that's exponential functions and then where you might see them. Logarithms they're a thing because they are inverses of exponentials. They undo exponential functions. That's why we have them. So e to the y equals x if and only if the log base e of x equals y, and the log base e we often write with the ln of x. So let's see, what's another way we could look at this? The log base 2 of 8. What does this equal? So the thing you would ask yourself is 2 to what power equals 8? So 2 to what power equals 8? And so the question mark is 3. That's how a logarithm works. So e to the y equals x would be the exponential way of writing that. All right. So properties of, I should draw what the pictures look like. So remember our exponential functions, they look like this. This is an exponential. So a logarithm is an inverse of that. So it's going to flip over this line, a reflection over the line y equals x. So it looks like this. That's the log base b of x. I don't know what b is, but there you have that. So the domain of the logarithm, this is this guy over here, is going to be 0 to infinity. The range is all real numbers, negative infinity to infinity. These are swapped from what happens with exponentials because they are inverses. This has a vertical asymptote at x equals 0. The x-intercept here is 1, 0 instead of 0, 1 because those things have swapped places. These are properties of logarithms. The ln, or the natural log of m times n, you can split up to the ln of m plus the ln of n. Multiplication on the inside, you can split into two logarithms with addition. Division on the inside, you can split into two logarithms with subtraction. This exponent, we can actually put it on the outside. So we can write this as the ln of m to the r. And then even further, we can drag that guy all the way down in front and it doesn't change anything. So there are two ways you can sort of rewrite the ln of m to the r. The ln of m equals the ln of n if and only if m equals n. The ln of 1 is 0. Look back here, this is the ordered pair 1, 0. So the ln of 1 is 0. The ln of e is 1. Those undo each other. So the ln's undo each other, and that exponent of 1 comes down the front. The ln of e to the x is just x. They cancel each other out because they're inverses. And then the ln of e to the x is just x. So e, whoop, that's not an e to the ln of x. The e and the ln cancel and you get that x back as your answer. That is property number 11. But 10 and 12 are the same property, just with x equal to 1 in number 10. All right. So there are some properties we're going to use to rewrite these logarithms, and that'll help us. You can maybe see where this is headed. It'll help us take derivatives. If we can do this sort of thing, that'll help our derivatives get easier. All right, so we're going to rewrite this to a single log. Okay. So I'm going to move this 2 up here. So we have the ln of x squared plus the ln of y. This is addition, and with 2 logs, so I can squish it together with multiplication. So this would be equivalent to the log, the ln of x squared times y. That is the reverse of this property. And then I also use this guy. Maybe I should write that. Number 7. And then number 5. All right. Let me pull that list up so I don't have to keep scrolling. Now, on this one, we have addition again and 2 logs, so we can squish it together with multiplication. So x plus 1 times x minus 1. And then I'm going to go ahead and simplify inside of there. So that is first, outer, inner, last. So we're looking at the ln of x squared minus 1. And that is, again, property number 5. And then just algebra. Okay. And then on this one, we have the ln of x minus 4 minus the ln of 2. So we're looking at subtraction with 2 logs, so we can squish that together with division inside of a log. And that is property, what, 6? Number 6. This one, the subtraction outside, 2 logs, you can make division inside of 1. All right, woo, got a lot going on in number 4. We are going to first fix these powers, push them up here. So I have the ln of x plus the ln of, that's x plus 5 to the 1/2. I'm just going to make that the square root of x plus 5 minus the ln, again, for the same reason, the square root of x minus 3. And then this is addition inside of a log, so we're going to make that multiplication. So the ln of x times the square root of x plus 5 minus the ln of the square root of x minus 3. And then we are going to because this is subtraction with two separate logs, we'll use division to combine them. So x times square root of x plus 5 over the square root of x minus 3. There was a lot happening there. So what is this one? This first step was number, which one's the exponents one? Number 7. And then to get to this step, sorry, let me rewrite this. This was number 7. This was number 5. This is number 6. Okay, now we're going to go the other way. We're going to expand these things. So the reverse of those things. So this is like m over n on the inside. So you're going to do the ln of 5x minus the ln of y. It's hard to know when you're done with these, but this first piece is the ln of 5 plus the ln of x minus the ln of y. And we're done there. On this one, we have this thing is actually power of 1/2. So you're looking at the ln of 2x plus 3 to the 1/2. We're going to push that down in front. So you have 1/2 the ln of 2x plus 3. And then leaving that 1/2 outside, we can split up what's going on here. No, we cannot, because that is not multiplication inside. We're done. So this was what, number 6 here, and then number 5. This is number 7. All right. Again, because this is addition inside of here, not multiplication, we are stuck. We can't do anything else. This one, I guess, technically you could stop here because that is addition, but we can factor that. Sorry, I should use green. This is the same thing as the ln of what, x plus 2x plus 3 times x plus 3. No, that doesn't get me to 5 on the end there. 5 and 1. Yeah. So, but this is a product now, so you can make this the ln of x plus 5 plus the ln of x plus 1. And this is just factoring. And then this is number 6. Oh, same one we keep using. Is that 5 or 6? 5. I meant number 5. Okay. Number 8. We have a fair amount of things going on there. We are going to, the division is the first thing that I see. So we're going to do the ln of the 4th root of 3x minus the ln of x times y to the 4th. I'm going to split this second piece. So I'm going to put big brackets here. So the ln of x plus the ln of y to the 4th. I'm leaving that first part alone. I'll go back to it in a minute. So I'm going to distribute this negative to here, and I'm going to bring this 4 in front. So I'm looking at minus 4 times the ln of y. So the second part is done. I need to figure out what's going on with that first piece, that first bit. So this is a power of 1/4. So I have 1/4 times the ln of 3x. And then I'm going to make that 1/4 big, and the ln of 3 plus the ln of x. And that should be good to go. I guess you could work at combining like terms, but I think this is great. Okay, so expanding, condensing, just use those properties, have them nearby. Excuse me. Have them nearby so you can look at what to do where. All right, so then using those ideas to solve equations, we are going to use the fact that, so the ln of e to the u is just u, and e to the ln of u is just u, because those undo each other. So we're going to use that here. So we'll put remember. All right, so we're going to try to get e to that thing by itself. So we're going to divide everything by 2. So I have e to the 2x plus 1 equals 13. And what we're going to do is use this property here. We're going to take a natural log on both sides. So like if this was the square root of x equals 2 or something, to get x by itself, you would square both sides, right? So those undo each other, you get x equals 4. So the idea is really similar here, that we're going to, because the square root of x and squaring a thing are inverse operations, so are the natural log and the exponential. So you are taking a natural log on both sides. So we have the ln of e to the 2x plus 1 equals, if you do something to one side, do it to both sides. But these cancel, and we can bring this exponent down front. So we have 2x plus 1 equals the ln of 13. And then we're solving for x. So 2x equals the ln of 13 minus 1. And then x equals the ln of 13 minus 1 divided by 2. So that would be your answer there. Okay. Similarly here, we want to get e to the whatever by itself. So we're going to divide both sides by 6. So we get 8 equals e to the negative 0.4t. And we're going to do the same thing. Take a natural log on both sides, because that'll get rid of the exponential term and allow us to pull that negative 0.4t down in front as a constant or as a multiple. So these cancel and we bring this down. So we have negative 0.4t equals the ln of 8. So t is going to be the ln of 8 divided by negative 0.4. All right. Here we are looking at a log. We're going to condense first each side of this thing to a single log, and then try to, we'll use one of our properties. So this is addition in 2 logs. We can multiply. So x times 2x equals the ln of 18. This is the ln of x squared equals the ln of 18. And we're going to go look at property number property number 8. The ln of m equals the ln of n if and only if m equals n. So that's what we're looking at here. 8, that m equals n, or x squared equals 18. That is a 2x squared. I'm sorry, I dropped that 2. So x squared equals 9. So x equals plus or minus 3. Negative 3 doesn't make sense, so it's just x equals 3. Negative 3 doesn't make sense because when you plug in negative 3 here, the ln of a negative number is undefined. Oh, is that true? Yes. Yeah, okay, good. Just, oh yeah, right, because just the ln of x looks like the shooting star kind of that starts at the x-axis. Yeah, a y-axis. Okay. All right, so just x equals 3, then we'd solve that equation. All right. Goodness gracious. Okay, number 4, we have subtraction. So we're going to use division. The ln of x squared plus 2x minus 3 divided by x minus 1. This is inside one log. I'm going to factor that. That is x minus 1 times x plus 3 over x minus 1. And that equals 2. I'm going to cancel that. So I'm looking at the ln of x plus 3 equals 2. Now remember that e to the ln of something equals that something. So this is what we're going to use now. We're going to exponentiate, or that's what this is called. So we're going to make each side a power of e. So what happens on the left-hand side is those cancel and you get this guy. So x plus 3. On the right, we have e squared. So then we're looking at x equals e squared minus 3, which is approximately 7.389. Okay. Number 5, our last one. A deposit of $5,000 is made into an account that pays interest at an annual rate of 9.6%. So R equals 0.096. And P is $5,000. Maybe I should write this somewhere else, but find the time required for the investment to double. So that would mean the accumulated amount was $10,000. Compounded quarterly or compounded continuously. So A, we're looking at compounded quarterly. Okay, so we have A equals P times 1 plus R over N to the NT. We are looking at here, $10,000 is our accumulated amount because we want it to double. And the initial investment was $5,000. 1 plus R, which is 0.096 over N. It's compounded quarterly, so this means that N is 4. And then to the 4NT, so 4T. That's the thing we don't know, and the fact that it's in that exponent is what requires us to understand logarithms. So to start with, we're going to solve for t. To start with, the reason we're solving for t is because it says to find the time required. So divide by 5,000 to start with. So this is 2 equals 1, and type that into a calculator. The inside of that is 1.024 to the 4t. Okay, so we need to get this out of the exponent. So we're going to take a natural log on both sides. So the ln of 2 equals the ln of 1.024 to the 4t. We can pull this down front. So you're looking at the ln of 2 equals 4t times the ln of 1.024. We're trying to get t by itself, so divide both sides by 4 times the ln of 1.024. So we have t is that the ln of 2 over 4 times the ln of 1.024. I don't know what the approximation is for that. Yes, I do. This is 7.307. So it'll take about 7 years. Compounded quarterly, but let's do it with, I wish I had written this better. Here, I'll fix it. Let's do it with compounded continuously right next to it here so we can get everything in one spot. Okay. Whoa. All right. Move this over so I have some space. Okay. So for B, we're looking at compounding continuously. So you're using A equals PE to the RT. The accumulated amount is $10,000. We initially invested 5,000. Our rate is 0.096, and the time is the thing we're looking for. Divide by that 5,000 to start with. So we have 2 equals e to the 0.096t. And remember, the ln of e to the something equals that something. So we're going to take the natural log on both sides. So the ln of 2 equals the ln of e to the 0.096t. These cancel, we're left with this. So the ln of 2 equals 0.096t. Divide by 0.096. So t is the ln of 2 divided by 0.096. So t is approximately 7.22. So it'll take less time, which makes sense. Okay, so that is sort of a quick review and recap maybe of exponentials and logs that hopefully you got in college algebra, and then some of the application problems that we're going to be solving and taking derivatives and solving and stuff next week or next time for 5.3 and 5.4. Thank you so much. Let me know if you have any questions.